Thank you very much, Peter. Thank you very much, Jörg, and good afternoon also from my side. So it's my pleasure to introduce the activities of my laboratory. Our main focus currently is on battery research. We joined the SCCR storage at the beginning of last year, so we are one of the younger players aboard the team. We are focusing here in work package 2 on the development of advanced batteries and battery materials. Our task is the development of next generation lithium-ion batteries. In this project we are collaborating very closely with the group of Maxim Kovalenko and his people. They are specialized in the anode development, where we bring in our expertise on the cathode side, and also more recently we are focusing also on the electrolyte development. So when we started the project, the state-of-the-art was defined to be, for lithium-ion batteries, at 220 watt-hours per kilogram. That's on cell level. You should always distinguish between cell level, materials level, or system level. This is on cell level. And the target that was defined for our team was to reach 275 watt-hours per kilogram by the end of the SCCR phase 2. Just to give you a bit of an idea what these values represent, I just show you here a data sheet of Panasonic. So this is the top of the line battery that they are offering. These 18650 cells, they are 18 millimeters high, diameter, 65 millimeters high. That's the batteries that go in many of the portable computers, and these batteries became particularly famous because they're used in the Tesla cars. Panasonic, LG, and Samsung, they have all the different labels, but they all produce batteries of this type. But this is one of the top-notch batteries with an energy density currently of 243 watt-hours per kilogram. Now, if you look a little more in the charge characteristics here, down here, you can see that the battery is first charged at constant current, so the capacity increases linearly. This takes about a little bit less than 2 hours, but after 2 hours, the battery is put in constant voltage mode because you cannot exceed a certain voltage for safety reasons, and the battery is soaked for another 70 minutes here, where you get another 10% of capacity, which is probably not always a very useful capacity for the application. But that's the way to get to this 243 watt-hours per kilogram. So if you subtract about the 10% of that extra capacity, you're back down to 220 watt-hours per kilogram. And just to give you an idea of what is the benchmark for us, the starting part for the SCCR project. So the level is quite high. We are basically trying to compete here with the top level of industrial manufacturing, and in the PV community that will probably be called the world records, just to compare on the level. So the battery don't maintain this high energy density over the battery lifetime. You can see here the cycling life. So after 500 cycles here, the battery is down to 70% of its initial capacity. And Tesla drivers are always shocked when I tell them that after 500 cycles, your battery is down by 70%. That's not fully true, because what Tesla is doing, they're limiting the range of charge and discharge. And you can see this here. When you limit, for example, the depth of discharge from 6 to 94%, you can extend significantly the lifetime of the battery. So that's a trick that everybody's using, which makes it also very difficult to compare different battery products from different manufacturers and put them on the same level, because it depends very much on the history and how the battery is cycled. Okay, so I think retrospectively, I feel we were maybe a little bit naively to commit to such high energy densities, but nevertheless, we are up to the challenge. So the first part, of course, how can we reach 220 watt-hours? Just the starting part of the project. So in our lab, we started on the material side. So we built an automated co-precipitation reactor for the synthesis of cathode materials. You can see electron microscope image of these materials here that we synthesize. Actually, we are synthesizing smaller particles of the size of about 100 to 200 nanometers, but we are aggregating them into larger particles using a hydrodynamic process. And it's important that we cluster these particles in larger particles, because that reduces the effective surface of the particles, so we reduce surface reactivity and thereby get better and more stable performance. In addition, these particles have a better packing density, so we can pack more material per volume in the electrode. So in a first approach, we validated our synthesis routes, trying to synthesize this NMC111 material sheet. This stands for nickel, manganese, cobalt in a ratio of 1:1:1. These are layered oxides with lithium inside. These were commercially available already 2 years ago. And so we had basically a comparison, how good is our material to what is established on an industrial level. This is the result here. We get out about 150 milliampere hours per gram of material You can see this here as a function of cycle number, and the C rates here, they represent at what discharge rate and charge rate we are cycling the battery. So C over 10 means charging and discharging the battery in a period of 10 hours, and then at faster C rates here, this is only 1 hour charge and discharge. You can see we lose a bit of capacity. That is typical for battery materials, but our materials are comparable to what is available from industry. So the problem is when we now work on lab cell batteries, we typically make electrodes, typically a square centimeter in size, pack them in something like a lab cell battery, something that can look like coin cell batteries you can buy from Igor or Coop. And when you then try to assess what's the energy of the cell, well, you get relatively low values. The point is that the packaging in lab cells takes a big part of the battery, and this is actually an optimistic approximation here because I did not include the excess of electrolyte that we usually use in lab cells. So in order to improve the energy density here, we had to put quite some effort in the coating process on the level of slur formulation, tape casting, drying, calendering. This is not a scientifically very rewarding task. It's a lot of trial and error, but we have to go through that way to get to better cells. So you can see the results here. So now I'm not reporting milliampere hours per gram, but now per centimeter square. So this is how much charge can we bring on a current collector per centimeter square of current collector. And we were starting out here with pretty academic mass loadings of about 3 milligrams per square centimeter. They result in about 0.5 milliampere hours per centimeter square. But you can see we managed to improve the aerial capacity by about a factor of 10 here, reaching aerial capacities larger than 4 milliampere hours per centimeter square. And what is very important here to notice that our rate capability is still quite okay for these cells. Okay, so the challenge is now going from half cells, where we use lithium as a counter electrode, to graphite from Maxim Kovalenko's group. They also developed high mass lithium graphite electrodes. And the problem in full cell is that the lithium that you have available now is coming exclusively from the cathode. So you don't have any excess lithium that you can pump into the system. So if you lose this in some parasitic processes, it's lost for cycling. But you can see here, we were managing to basically have an initial aerial charge capacity, which is quite high, still in excess of 4 milliampere hours per square centimeter, and have here over 300 cycles some fading, which is also seen in the Panasonic cell, but which is quite okay, I think, for an academic cell. So with these improvements, we bring the energy density about up to 150 watt-hours per kilogram. So this is still lower than the 220 watt-hours that we need to achieve. And the missing piece now is provided by Axel Fürst's group at the Fachhochschule in Burgdorf. Because currently we are basically just using one anode and one cathode, so we need stacking several of these electrodes on top of each other to basically amortize the weight of the packaging and increase the energy density. And so this is a projection that we did with the same values that we have here in our lab cells. You can see if you go up to 11 layers of stacks here, we can reach an energy density here of about 200 watt-hours per kilogram. So this cell is not yet a reality, but we are working it towards that direction. Okay, so I showed you how we can reach just the starting point of the SCCR. So that took us a little more than a year to get to this point, and we are not yet fully there. But how do we get any further? So we have to reach 275 watt-hours per kilogram by the end of the SCCR. So the approach we have been choosing, we've been going back to the materials level, the synthesis level, and we are now focusing on increasing the amount of nickel in the cathode materials. You can see here, this is the gravimetric charge capacity again for NMC 101. So where nickel, manganese, and cobalt are in a ratio of 1, 1, 1, and 1, so 30% each. And we are increasing now nickel content to 80%. This has the advantage that we are increasing here the charge capacity quite significantly by about 30%. At the same time, we are using the cobalt content. And cobalt, you may be aware that it's classified as a critical material by the European Commission because of its high supply risk and high economic importance at the moment. So the prices are also increasing at the moment quite fast. And so reducing the cobalt content also allows you to have a cost reduction. The problem now with nickel-rich cathode materials is that their stability is much worse than in the NMC 101 case. They have much higher surface reactivity and lower intrinsic stability. And you can see here, if you just put these materials now in a standard cell, which works well with NMC 101, we have a very rapid fading. So we have been looking into sacrificial electrolyte additives, which we can decompose during the first few cycles, which then form a protective layer, and we were able to stabilize the NMC801 cell here with a capacity retention of 90% after 200 cycles. That's our best result at the moment. We're still suffering from impedance growth. We're also not yet working at high mass loadings, but we're trying to improve this over the next few months. Ultimately, you can see this is the projection again, but now for the NMC811, and with this we should be able to reach 275 watt-hours per kilogram. And Josefa and Gian, they presented before a poster on this topic in the poster presentation. I want to also present you 3 other topics we are working on, 3 other projects. Quickly just give you an overview on this. They are not part of SCCR, but related topic-wise. Giorgio pointed out already that safety in the battery field is very important, and one of the main risks in lithium-ion batteries comes from the organic electrolytes. These are highly flammable materials, so if you have a thermal runaway, you basically you run into a fire. And so what we are looking into is to use electrolytes which are non-flammable. One approach that we are looking at is to use water as an electrolyte. Of course, water has a problem. Water has an electrochemical stability window which is limited to thermodynamically to 1.23 volts. If you go to lower potentials, you evolve hydrogen. At higher potentials, you evolve oxygen. You want this in an electrolyzer, but definitely not in a battery. So the trick that Darwin and Ruben are using, they are going to very high salt concentrations. So when you are reaching these very high salt concentrations, basically there's almost no free water left, and all the water molecules become part of the first solvation shell of the cations. You can see this here in the signature of Raman. I don't have time to explain this in more detail, but there's a clear structure change in how the water behaves. This allows us to improve the electrochemical stability window here quite significantly. So we reach a stability window of about 2.6 volt. That's not yet 3.7 volts like in a lithium-ion battery, but still an improvement. And this allows us to cycle now reversibly anode and cathode materials which are outside the stability window of water. David has managed to stabilize this cell now with a capacity retention of 77% after 500 cycles. This is slightly better than Panasonic in terms of the cycling stability, but of course at lower energy density. So we are here roughly at an energy density which is comparable to lead-acid batteries. We think that it's important to use sodium in this case because we use very high salt concentration, so we don't want to use lithium in the case, and we believe that this also could reduce the cost of the assembly because you don't need any inert atmosphere to assemble these cells because they are basically stable also in humid environment. So David received the poster award at the ECS Spring meeting this year for his work, and also pitched his project at the Falling Walls Lab, the Swiss qualifying, receives here the first prize award from ETH Vice President of Research Detlef Günther, and will represent Switzerland now at the final, at the global finals of the Falling Wall Labs competition in Berlin coming up in November. The other approach you can use to make batteries more stable is, of course, to replace the liquid electrolytes completely and go to a solid electrolyte material. So within the CTI project we had together with FZ Sonic, our partner, we've been looking quite in detail into the sodium beta prime alumina that Giorgio presented and introduced before. These are ceramic electrolytes which have a very high conductivity. You can see here 200 millisiemens at 300 degrees C, so they make them very ideal for high temperature batteries, sodium nickel chloride batteries produced by FZ Sonic, but also sodium sulfur batteries produced by NGK in Japan. We believe these materials also have potential because you can see the room temperature conductivity is also relatively high at 25 degrees C. So they could also eventually be used in next generation solid state batteries that may come up in a few years. So within the PhD thesis of Marie-Claude, we looked at how ionic transport is related to microstructure. You can see here as a function of sintering conditions at a lower temperature, we get relatively porous structures where the sodium ions have to follow a tortuous path to reach the other side, so the conductivity is relatively low. And then we were able to demonstrate the existence of a liquid phase formation at temperatures above 1500 degrees. So this liquid phase promotes densification of the material. You can see all the points above have a density about above 97%. And in these materials, it's the grain size which dominates the ionic conductivity. We're also looking at more exotic solid-state electrolyte materials. For example, these closoborate salts here. These are salts with complex anions. You can see here there are different clusters of boron atoms. They're closed shell, either B10s or B12. They're the most stable ones. It was already known in the literature that when you heat these materials to a higher temperature, they undergo a structural phase transition and to a higher symmetry state, which has a higher ionic conductivity, which is in the range which we would expect, which we need for making a battery. So we were able, you can see that this phase transition also leaves this trace here in the colorimetric measurements where you can clearly see an endothermic signal. But we were able, by mixing these two anions into this FCC lattice, we were able to completely suppress this transition. And this happens exactly at a ratio of 1:1, and that's for a specific reason. We were able to stabilize the high symmetry phase of these materials already at room temperature. What you see here is simply the extension of the Arrhenius behavior of the high symmetry phase. So we're having now solid-state electrolyte with an ionic conductivity of about 1 millisiemens per centimeter at room temperature. So this enables us to develop a battery. So we looked at the electrochemical stability window of this electrolyte. You can see these measurements here. So we have oxidative events here above 3 volts, but below we are pretty good. You can see also these are very small currents, nanoamps per centimeter square. So this is important to look very detailed. We don't want to do milliamps per square centimeter like people do in electrolysis. We want the opposite here. We want a stable material. And you can see here, at very low voltage, we have a sudden increase of current, and that has to do with the plating. So we are plating sodium on the current collector. That means our material is in principle compatible with a sodium metal anode. And you can see here we did extended stripping and plating experiments for 2 weeks, stripping sodium and plating sodium reversibly without any significant increase here in overpotential. So to build a full battery, we then joined the sodium metal anode shown here. We needed a separator, which is just our pure electrolyte. And then for the cathode side, we were choosing to use sodium chromium oxide as a cathode material. And in this cathode part, we have to basically mimic the porous structure of an electrode, which is infiltrated typically with a liquid electrolyte. But here we have to mix the solid electrolyte with the cathode material, and we were able, with this concept here, to stabilize a solid-state battery for 250 cycles with a capacity retention of 85%, which brings this type of material to the technology readiness level where other solid-state battery concepts are around. And so our PhD student Leo is currently on an exchange program working at Hanyang University with a very renowned group in the field of solid-state batteries to bring this concept even further. And we were presenting our results at the MRS Spring meeting in Phoenix earlier this year, and we were approached by Samsung, who is now also evaluating this type of materials for their batteries. Okay, I want to close my presentation with just giving you the remark that currently I feel that there's a high level of expectation from society for new battery technologies. Nevertheless, I think it's always important when you read news in a newspaper or so that is saying about what's the technological maturity of the different concepts. So it's probably fair to say that all solid-state batteries still need a few years to become a commercial product, although some people would like to have all solid-state battery available already yesterday. Okay, just as an information, we also give we are offering a practical lab course to ETH students. They come to our lab, synthesize battery materials, integrate them in batteries, and do their analysis. We have several postdoc positions open to be filled by the end of the year, about 3 positions. So if you're interested, please contact me. And I would like to thank our partners, in particular also FZ Sonic, for giving the presentation today, and our funding agencies that support us. And I'm happy to take your questions. Thank you.